Hello everyone. So today we're going to continue on 11.1. So last video we get to solve this equation and we come out to be the solution to be this. So I do want to show you how this solution work. So we can definitely do a quick check of how the solution work before we move on. So oops. So here's my differential equation. And we're claiming that our solution is c1 e to negative 3x plus c2 e to negative 2x. And it's actually interesting to see how this actually work out. The idea here is that if I know this is y, then y prime would just equal to negative c1 e to negative 3x minus 2 c2 e to negative 2x. So now notice I didn't combine this because if I combine this, that will become a different constant than C1. I would rather actually keep track of how this constant relates to C1 because it's relating specifically. Okay? And I can do second derivative that would equal to 9C1 e to negative 3x plus 4C2 e to negative 2x. So now I'm going to combine this thing together and see what happens. So y double prime plus 5y prime plus 6y would equal to 9c1 e to negative 3x plus 4c2 e to negative 2x plus 5 times negative 3c1 e to negative 3x minus 2c2 e to negative 2x plus 6c1 e to negative 3x plus c2 e to negative 2x. Now, here's something interesting that I want to point out. Notice that the way it's structured, the way the solution is structured, is that once I have this solution right here, its derivative and its second derivative are simply formed by the same exact two function, e to negative 3x and e to negative 2x. And so the only thing that technically changed is basically the coefficient in front of it. And therefore, what happened is we try to make the coefficient in front to somehow, in this case, balance out so that we can get the 0. That's how that works. So let's see if this actually happens. So if I look at this correctly, that's 9c1 e to negative 3x plus 4c2 e to negative 2x minus 15c1 e to negative 3x minus 10c2 e to negative 2x plus 6c1 e to negative 3x plus 6c2 e to negative 2x. So therefore, there are basically two types of terms here. Oops. And notice that would be 9 minus 15 plus 6. That's 0. And 4 minus 10 plus 6. That's also 0. So this kind of will be 0 c1 e to negative 3x plus 0 c2 e to negative 2x. And therefore come out to be 0. Okay? So that's how the solution come about, because the idea here is that I need to plug in this set of function y and its derivative, and yet I have to get some kind of fixed output out of it, in this case 0 output, and therefore it forces the way it works is that all these function e to negative 2x and e to negative 3x would get cancelled out. And that's the only way for it to always equal to 0 regardless what the independent variables are. So hopefully that showed you how to solve a differential equation, second order differential equation, especially a constant coefficient one. Now, but of course, here comes the big problem. The problem is that notice that the process is, well, not that difficult for constant coefficient differential equation, but it is require a fair bit of work to do the exponential multiplier method. And the issue here is that doing a second order differential equation is not too bad. You just do exponential multiplier method twice. But what if we do third order, fourth order, 12th order? Then now it becomes a much longer process, because each time I do exponential multiplier, I'm adding more terms to my potential solution and therefore creating more words. And remember, a second order differential equation with two terms, a subspace of 2, But the third order will be a subspace of dimension 3 and dimension 4, dimension 5, and on. So how do we actually simplify this process and make it easier? Well, actually quite simple. If you think about it, you actually learn about it in chapter 3. Notice, based on the order of the differential equation, we know the dimension of the subspace that we're forming. Okay? A second order differential equation, the subspace will forming a solution set that is in the subspace of dimension 2. And in order to generate every single element within a subspace, all I really need is to come up with a basis. If I form a basis for that subspace, I would then be able to use that to form every single element inside. And based on what we learned in chapter 3, in order to form a dimension 2 subspace, to form a basis, all I need would be two elements within that dimension 2 subspace that are not linear dependent of each other. So if we can come up with that, then we're golden. We don't have to worry about forming anything else. All I need is to find two elements that would solve this differential equation. And if I can do that, I'll be able to form the solution set without any issue, without solving it. So now the question comes down to how? Well, the idea is the following. The idea is that these type of differential equation, constant coefficient differential equation, they always have what we call exponential solution. Okay? A constant coefficient, a linear constant coefficient differential equation always has exponential solution. In the form of y equal to e to the rx, or u equal to, or whatever independent variable you use. So therefore, we can take advantage of that and try to come up with the solution. Notice that if you think about it, our solution are definitely in this form. Is e to negative 3x and e to negative 2x, where we mean r is negative 3 and negative 2. And some of you are already clever and can probably realize what the negative 3 and negative 2 came from. But if not, then let's try to figure it out. So the idea is the following. If we indeed let y equal to e to rx be a solution, be a possible solution to our differential equation d squared plus bd plus c of y, then that implies the following. Equal to 0, I'm sorry. So I'm talking about homogeneous differential equation for now. And non-homogeneous also have that property, but it has something extra that we're going to have to talk about. Then it would imply basically the following. D squared plus bd plus c of y equal to d squared plus bd plus c of e to the rx, and that equal to 0. Now, if I look at this equation right here, notice what happened to this equation. D squared, so this becomes d squared of e to rx plus bd of e to rx plus c times e to the rx equal to 0. And if I do that correctly, when I differentiate e to rx twice, it basically just becomes r squared e to rx. Plus, this is b times r e to rx, because derivative of e to rx is r e to rx, and this becomes c e to rx equal to 0. What's interesting about it is the following. Since we know e to rx can never equal to 0, I'm going to go and just basically cancel them all out from my equation. And when I do that, I get this equation. This is a quadratic equation in R, of R. and therefore indicate that it must have two solutions. What a surprise that our solution to a second order differential equation has two, is dimension 2, because this equation has two solutions. This equation has a name. This equation often referred to as characteristic equation. And in this case, for second order differential equation, the characteristic equation is actually in R2. Is a quadratic, is second degree. And notice, in order to form the basis to our solution set, what I do need to do is figure out what R is, and now we have an equation to solve for it. So this equation, the solution to this equation, the solution to the characteristic equation also has a name. They are called characteristic roots. And they can be used to form the solution. They can be used to form the solution set of the differential equation. Before we formalize all of these into a theorem, we can definitely give it a try first and see how that works. Okay, so, but in this case, maybe I'll write out a little bit just so that the idea is the following. So suppose you have d squared, plus bd plus c of y equal to 0. So that's our differential equation. We can rewrite it into our characteristic equation. That will be our characteristic equation. And yes, this process can be done, can be expanded to higher order differential equation. That's what we're going to do eventually. But just, remember what I said, I cannot teach you everything in one day. So we'll go slowly work to that. And let's assume this equation would have two roots. Let's say R sub 1 and R sub 2. So these are called characteristic roots. And it would definitely have two roots. I know some of you are probably thinking, like, what if it doesn't have a solution? Or what if it repeats the solution? Well, we will talk about those. And it would not have no solution. When you say no solution, you are basically implying that have imaginary solution. And we will learn to deal with imaginary solution eventually. And one of this section will be imaginary solution. Let's see if I can show you. Notice complex solution, 11.2. That's where we're going to talk about that. But just not right now. But let's say we have two solutions, and therefore it would imply the following. It would imply that the solution set would be linear combination. So the solution set will consist of all linear combination. So basically the span of e to r1x and e to r2x. So therefore, meaning the solution will be in this form. And we'll formalize this in a theorem eventually, but show you how this works. So we can definitely try this. And you find out that doing this using characteristic root is actually very easy to do, because all you really need to do is know what the solution will look like, and then just find the information you need to plug it in. And to find the information you need to plug it in doesn't require any derivative at all. Remember, that's what we try to do, is try to solve a differential equation using as little integration or things like that as possible. So I'll give you an example. So we can definitely do, you can definitely try to redo the problem that we did, but I would rather go for a different one. So I'm going to ask you to solve a different one. How about solve this one? Y double prime minus 3y prime plus 2y equal to 0. Okay, so pretty simple equation. So what I'm going to do is we're going to go through the same process. I'm going to first rewrite it into differential operator form, and then rewrite it into my characteristic equation. And then this equation is extremely easy to do. That's just equal to y minus 2, r minus 2 times r minus 1 equal to 0. And therefore tell me that I'll have the two roots, r1 equal to 2 and r2 equal to 1. So those are my two roots. I usually list my root from largest to smallest, but it technically doesn't really matter. But just some consistency I will like. And so therefore now I'm just going to write out my solution. My solution, y would equal to c1 e to the 2x plus c2 e to the 1x, which is just x. And voila, that's my solution. Notice we didn't do any integration at all. We just literally just solve a quadratic equation for the two roots and then use them to write out the solution. All right. Now we can definitely try another one. So we can definitely try to solve this one. Let's say y double prime minus y minus 12y equal to 0. Y double prime minus y prime minus 12y equal to 0. So same exact way, I can basically do this. I can first rewrite it into differential operator forms. Now, here you could definitely write it into the characteristic equation, but you could also write it this way. You can also factor this first and say, well, that's just d minus 4 times d plus 3 of y. And therefore, basically, just turn this into r minus 4 times r plus 3 equal to 0. And therefore, r1 would be 4 and r2 would be negative 3. And so now I'm going to write out my solution. Y equal to c1 e to the 4x plus c2 e to negative 3x. Simple enough. Good. So now notice how easy it is to use characteristic root to solve differential equation. And as a matter of fact, it will probably be one of our most basic technique and most commonly used technique when we deal with this type of equation. And we will try to, when we try to solve a problem, like a word problem, we'll going to try to turn it into a constant coefficient differential equation and therefore make it a lot easier for us to actually do the problem. Now, this is probably the last thing I want to show you. Okay, and then that will be it for this video, and that will be theorems that summarize this process. So this theorem is theorem 11.1.1. This theorem will be expanded upon a little bit later on because while this theorem basically covers all cases, but we will have to also talk about what happened when we have complex solution. So that will be expanded on in 11.2. But for 11.1, we can definitely state the following. Let's say given a linear, maybe I should say this, a second order linear constant coefficient homogeneous differential equation. Homogeneous. In the form of y double prime plus by prime plus cy equal to 0. And once again, if you do have a coefficient in for y double prime, you just divide it out to the entire equation. Okay. Let's say its characteristic equation is r squared plus br plus c equal to 0 with, let's say, two characteristic roots. Let's say R1 and R2. So these are called characteristic roots. And there are basically the following two scenarios that we want to consider. Okay, number one, if R1 and R2 are unequal, that means R1 does not equal to R2, then the general solution to this differential equation is basically in this form: y equals c1 e to r1x plus c2 e to r2x. Or it could be t, depending on what independent variable you are. So that would work if r1 and r2 are not the same. Now, what if they are the same, which is a possibility? And now, notice that if the solution are real or imaginary, they would still fit into this category. If they're imaginary, they would have to be unequal. So therefore, have to be case 1. But if they're real, then there's a possibility that the two roots are either distinct, not equal, or they're equal. So what happens if they are equal? If R1 equal to R2, and we'll just simplify them by calling them R, then this general solution will be in this form instead. The general solution to the differential equation is in this form: y equal to c1 e to rx plus c2 x e to rx. So notice that because it's a second order differential equation, its dimension still has to be dimension 2. So therefore, to generate a second term, the solution actually will have an extra x multiplied to e to rx to form a non-linear dependent term to e to rx. That's very important, okay? So that would be how the solution look like. Now notice that both of these has C1 and C2. So what do C1 and C2 do? Well, those two values are uniquely identified by the following. The values for C1 and C2 will be uniquely determined by what we call the initial condition. And this is how the initial condition will look like by using the initial condition y of x sub 0 equal to some constant alpha and y prime at x sub 0 equal to some constant beta. Important to understand is that they're called initial condition because they are both at the same value and it defined, and one defined for y and one defined for the derivative. Okay? So, show you some very simple example, and notice that using theorem 11.1.1, basically transform solving a constant coefficient differential equation into solving a quadratic equation, which is pretty simple. So let's try this one. I'm going to go ahead and ask you to solve this. Y double prime plus 5y prime plus 6y equal to 0 with the initial condition, let's say y of 0 equal to 1 and y prime of 0 equal to 2. And some of you might already thinking, what if I'm giving you these two conditions but they don't have the same value? Like, let's say one is y of 0 and the other one is like y of 1 or something. Well, that is a different problem, and they're not called initial value problem, but instead they're called boundary value problem, which we'll talk about a little bit more toward the end of this section. So let's say I'm going to solve this. So this is an initial value problem. And the reason why I know it's an initial value problem because it have both same x value on the initial condition. So we can definitely solve this. So if you want to, you can definitely do this. So we actually already know the solution to this, but we can definitely go through this again. So here's my differential equation in differential operator form, which turn into this characteristic equation, which turn into r plus 3, r plus 2 equal to 0. So therefore I have my two roots, -2 and -3. So therefore the general solution would be y equal to c1 e to the -2x plus c2 e to the -3x. So now just a matter of solving for C1 and C2. Now notice what happened when I try to solve for C1 and C2. So I'm going to do y of 0 equal to 1. So therefore imply that 1 equal to C1 e to 0 plus C2 e to 0. So therefore give us this equation. Now to do y prime, I do need to find a derivative first. So y prime will equal to -2c1 e to -2x minus 3c2 e to -3x. So now if I do y prime of 0 equal to 2, that means 2 equal to -2c1 e to 0 plus, or minus actually, minus 3c2 e to 0. Notice that having initial value to be 0 is definitely a big advantage in this case because e to 0 power just go away. So that's really good. Notice that from this equation, 2 equal to -2c1 minus 3c2. Notice what we have is a system of equation, more precisely system of linear equation. This become a system of linear equation to solve for C1 and C2, which is the reason why last year in multivariable calculus we talk a lot about solving system, because a lot of things we do here with multivariable calculus, even this single variable calculus, would require multiple constants to be solved, and they form a linear system when we do it. So solving this system should be pretty straightforward. I'm going to let you do that. And I'm just going to show you the answer to this. So if I'm not mistaken, in this case, C1 actually come out to be 5. And C2 actually come out to be -4. So you can definitely see that will work because that would be 5 plus -4, which is equal to 1, obviously. -2 times 5 is -10, minus 3 times -4 is plus 12, so -10 plus 12 is 2. So therefore, that tells me that the solution that we're looking for is this one. All right, I'm going to go and post a second example for you to try out. So how about solve this one? Solve the this equation, y double prime plus 2y prime plus y equal to 0, with, let's say, y of 0 equal to 1 and y prime of 0 equal to 0. So I'm going to let you solve this problem, and we'll go over this on tomorrow's video, as well as what I'm going to show you next. All right, I'll talk to you next video. Bye-bye.